We're going to look at a quick example here of calculating the period of a pendulum. Now remember, we talked in the video about the pendulum about the equations, the force, the restoring force of a pendulum. Restoring force meaning the force that brings it back into an equilibrium position. And we also talked about the period. This is what we're going to look at. The period of a pendulum depends only on the length of the string and gravity G. So here on the left, you can see I have a simple setup where I can get a pendulum to swing, and we can calculate its period using a stopwatch here. Okay, so first of all, let's set some things straight here. Gravity is 9.8 meters per second squared. We're on Earth, so that hasn't changed. The mass right now is 1 kilogram. Keep that simple. Then we want to talk about the length of the string. Currently on the left, notice here the length of the string is currently set to 0.7 meters. Then the period is going to equal 2 pi times the square root of the length, 0.70 meters, divided by 9.8 meters per second squared. So I'm pulling out my calculator so I can calculate this. There it is. So I have square root of 0.7 divided by 9.8 means that is 2 pi times 0.2673, and that'll be seconds. And so if I multiply that by 2 pi, so multiply by 2, multiply by pi, I get a period of 1.6793 seconds. Yes, I know I only need 3 significant figures, but you have 5 there just to be safe. Okay, so it's really hard to measure the period of 1 oscillation, so we're going to measure the period of 10 oscillations. That should take 16.793 seconds. And again, notice that this did not depend on mass at all. So we're going to lift up our pendulum, get it swinging, and then I'm going to start the timer when it's at the leftmost point. And there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I got 16.88 seconds. That is less than 1% error. So not bad at all. What would happen if I increase the amplitude? If I increase it to, say, 10 degrees, oh, that's 20 degrees too far. Let's go, let's see, I think I was around 10 before. Let's decrease the amplitude then. Let's go to 5. And on the left, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 16.79, that's perfect. That's absolutely exactly what we calculated. So the amplitude did not matter. If I go up here to 15 degrees, it'll come out to be the same. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 16.91, so not bad at all. As if you go anywhere beyond 15 degrees, and remember that was based on the approximation that sine theta is approximately equal to theta, and that is only true, and that's in radians. That's only true if theta is less than 15 degrees, whatever that is in radians. If you go beyond 15 degrees, then you start having much larger errors because our approximation is off. Now, let's change the mass. Let's make it heavier. Let's just go 10 degrees. Since we found out amplitude doesn't matter, we'll just go 10 degrees. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 17 or 16.74. If I change the mass to something really tiny, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 16.68. So we're consistently getting about the same value between 16.8 and 16.7, 16.9. It's what we're consistently getting, which is what we calculated, 16.8. So the period does not depend on the amplitude. It does not depend on the mass. It only depends on the length of the string. Watch what happens when I shorten the string. Period has definitely increased a lot. Makes sense because, the period has decreased. It's gotten faster. So notice here, length, if I decrease the length, then the period should also decrease, which it did in this case. But if I increase the length, you increase the period, takes more time for it to actually oscillate.